So this is question 5. Now, in this question we have a 1 second delay, and basically the system that we've used all along. Here the question is to look for the p-type controller interval for the system without delay, and then with delay. So we are kind of trying to get the feeling of what happens if we add some delay, which we have already touched base on, but let's see. Now, of course, we can again use R locus in order to determine the stability here. But we already know what the stability interval is of such a system. Just to quickly recap, we know that the stability interval is basically 0 and 7, because on the negative root locus there was a passage through the origin with k0, and if k is equal to 7, then we have a crossing through square root of 6. So basically the interval here without delay is 0, k, and 7. Now, what if we add the delay here? Now, let's have the delayed version where we calculate the transfer function in MATLAB using IO delay here, and that's 1 second, so GSD. Of course, here there's no method given, so you can just use whatever you want to calculate the stability interval. And I guess we should try the root locus one. So if we want to plot the root locus of GSD, which has delay in it, then you can see that this error message pops up. And it says that the root locus command cannot be used for continuous time models with delays. Use PuTTY. So it suggests us to use PuTTY to approximate the delay, but it is not possible to plot the root locus plot with systems that have delay in it. So, and the reason behind that is the following. In order to be able to plot a root locus, we need to know how many zeros and how many poles we have in a system. Now, delay is a strange phenomenon where we can't actually conclude the finite zero and pole amounts, because if we, for example, use the PuTTY approximation, gives us an approximate transfer function, and we can give it a degree. So the first degree is this, which has no delay in it. The second order PuTTY approximation would be this. Of course, we need this one here. So it has basically 1 0 and 1 pole in it. So if we have the PuTTY approximation of this IO delay, which is only the delay part and the first order, we can see that it places a 0 to the right half plane and a pole to the left half plane, and they are symmetric. If we increase it, it'll use the same polynomial with different signs here, which indicates that both of the zeros are on the right half plane and these are on the left half plane. So this goes on and on. If I go ahead and use, for example, 10 here, I get a large transfer function. Now, if we use ZBK in order to determine what the poles and zeros look like, you can see that there are these conjugate pole pairs, and when I increase it, it will just approach the delay transfer function. So basically, we can think of the delay as infinitely zeros divided by infinitely poles. Of course, this is just a reminder that this is not exactly true, but you get the idea. So you can't have a root locus plot of this. So what can you do? Well, basically, you can approximate it and then have a root locus plot, and that would give you an idea. So we could, for example, try to use that. So we have GSD. So what we can do is we can open up a figure, and then let's have, hold on. So let's plot the root locus of the putty approximation of GSD1. And I'm not sure, but I should be able to give it a color. And let's have another one, blue, with the second putty approximation. And let's see what it looks like. Round 5. So we have this. Of course, since we have them on top of each other, it is quite difficult to see. So let's get rid of the colors then. There we go. There we go. Now we have two different root locuses, which is concerning on its own, and they should give us some intervals, and these intervals would then hopefully correspond to the interval of the system with delay. Keep in mind that this is basically an approximation, so we're not quite sure about it. So I can determine that this is basically the point of j omega crossing. So I can see that the gain is equal to 1. So already I dropped down from 7 to 1. So I've talked about this in the video where we had to add some delay and then have a closed loop. So the stability intervals did shrink quite much, and at this point I'm curious about the interval that will be determined from this plot here. Now, one of the branches here crossed at a very high gain, but the other one crosses approximately at 97, 98, sort of. So I can see now that the higher the putty approximation degree is, the lower the gain value becomes, for this system especially. Now, of course, in terms of step responses, let's see what these step responses look like, so you get a feel of the approximation. So let's have the step response of GST with black dashed, for example, and then the putty approximation of GST at the first, or maybe let's repeat this for the second one with blue. Now, it's quite problematic. Let's try to zoom in here. Yeah, of course we have a an integrator here, so that's quite an issue. So we do have an integrator, so therefore we have a ramp response here. But you can see that the first order was red, and for the red here, the dashed one and the red one do not look alike in the transients, and we can also conclude that the blue one here, so the second order approximation, does kind of does a better job, but it's still nothing. So maybe let's have a very high level putty approximation, and let's try to examine this behavior. Now at this point you can see you need a very high approximation, putty approximation, in order to get the transients. So the similarity between the blue one and the dashed black one, there are still some minor differences, but it's way better than the first order one. But the pole zero map, if you also look for the pole zero map here, you'll see that the 20th order body approximation has too much poles and zeros. So in a way, you're modeling it with high accuracy, but then it's also pretty much useless to have such a high order system with so many poles and zeros. So there is a trade-off, and most of the time we use the first order and second order equation here. So, of course, if you have to do this on an exam, then what you have to do is you have to acquire the Pareto approximation. Let's say GS1 equals the Pareto approximation of GSD. You can look up the formula for the Pareto approximation. You don't have to use MATLAB. It was something like minus 0.5 times 1 and 1. I guess this was the formula for the first order one. So this would be the Pareto approximation. Let's check if it's true or not. So this would be then positive. This is basically tau, but tau is here 1 second. So this is the amount of delay times 0.5. Now this should give us minus 2 plus s, or in ZPK. This is basically this, and we've seen this before. So you can write this down and then multiply it with your original system. And then what you have to do is you have to basically convert it into a symbolic expression in MATLAB, but you don't need that if you have a pen and paper. So TF2sim, GS1, and then we would have TSS1, which would be the closed loop, since K rail, and then as usual K times GSS, and then 1 plus K times GSS, and then the numerator and denominator of the characteristic polynomial. I can also name it like this, num then of TSS1. So the important part here is to form PCS, which is, by the way, quite straightforward. If you multiply this and this, both fractions, you will get a fraction, and you use the numerator times K plus the denominator, and that's it. That's the shortcut. So yeah, this should be GSS1. Now we have a polynomial here, and what we can do is at this point we can look for the root table, Rotorus criteria, or we could plug in s equals j omega as we've done before. Let's try that part. So p omega subs, instead of s, we should use 1i times omega, since omega real. So it is possible to make the substitution with a pen and paper, because you can just have j omega to the fourth, which should give you omega to the fourth, and then minus j omega cubed, etc., etc. So now at this point, let's get the real part of p omega and then the imaginary part of p omega. 5, and you can see there are two expressions. Now, as you remember, this should be equal to 0 individually. So let's form our problem and say that the real part should be equal to 0 and the imaginary part should be equal to 0 simultaneously. Now this should give us a set of solutions. Now you can also see that, again, we have omega equals 0 here. If you factor that out, you have 6k minus 12 plus 9 omega squared. So 9 omega squared. And then the one on the top would then also have minus omega to the fourth. It's basically, this this one here. So this is equal to 0 and this is equal to 0. So as far as I can see, we should multiply this equation by 2 and then sum them together. So this would give something like minus 24 plus 18 omega squared, and then we would have plus 20 omega squared, and then minus omega to the fourth, and that's basically it. So this would be your final equation, and of course this is 38. So in a two-step process, we should be able to calculate the roots of this. You can also take out this minus here, make this a plus, this a minus, and then maybe move it to its actual position. Now we can see that this gives us basically a squared minus 38a plus 24. You have to solve for this. Once you have acquired a, then you take the square root. Of course, a should be positive. You take the positive solution, and then you take the square root, and again you take the positive solution, and that should give you the omega. Once you have omega, you can then substitute it in and see what the value should be, the k value should be. So it is possible to calculate it by hand, as you can see. And of course, we have many solutions, but one of them is basically negative. The other one seems to be negative. So both negative ones should go because omega should be positive by definition. So let's see. We have also k val dot k. Maybe we should also convert it into double. There we go. So omega val and k val. There we go. Now we can see negative, negative, they should go. We have 0, we have 6.11 and 0.8015. So of course, now we should get rid of the unnecessary values. Omega val should be positive. For those indices, we should reduce it to done. So let's see what k val and omega val should be. Now we are reduced to 2 of them, and we can also see where the crossing happens. Now for minus 54, we have a omega value of 6, and for positive value 1.03, we have omega 0.8. Now we can conclude that the stability interval is between 54k and 0.8015. Of course, we have to have the root locus here also. So let's create a figure, a subplot, root locus of GS, or the Putty approximation, GS1 here, yep, and the negative root locus. So this should be the second one and this. Of course, we should type it. So. And yeah, minus negative. So minus GS1, of course. There we go. Now, as you can see, we have a j omega crossing here and j omega crossing here. So omega is 6 for the negative one. It seems to be all right. And omega is 0.8 for the positive root locus. So we can see that the interval is minus 54 and 1.03. Of course, we have to increase the degree here. For 2, for example, we would do the same here. We would solve it. We would substitute. So you can see that this is basically adaptable. So it should work for higher order 2. Now we have a bit more. So we can see that there are 2 crossings for positive k values. One is 0.9970 and omega is 0.77, and then 308 for 11, and then there's also a negative interval, which seems to be a narrower interval. What we found is basically minus 12 point something, and then seems to be 0.9970. So yeah, I'm not sure about this. This most of the time becomes a higher interval. Maybe there's a numeric thing going on here because of the higher degree of the equations. So this seems to be 1 point something most of the time, but I'm not quite sure. But the only thing that I can conclude from the Putty approximations is I cannot still say that this is the actual stability interval of the system with delay, because it's not possible to conclude such a thing. The only thing that we can conclude from this here, from the Putty approximation and then the root locus method here, is that the instability occurs at the opposite of this. So basically what I mean by that is in the interval of 0.99 up to infinity and minus 12 up to minus infinity, the system is not stable. So I can say that if the Putty approximation is stable in interval, let's say AB, the system, the original system, is not stable in minus infinity, Ka and Bk infinity. And that's it. That's basically it. So now even though you have a higher order Putty approximation, you can still not conclude that the interval is the actual interval of the system. What you can conclude is that it is a upper bound on the interval, so there might be a little a small interval that does not belong to the actual delayed system's stability interval, but it lies between these two bounds. So that's basically it. Now, we have also a frequency method where we can determine what the stability interval is, and it's quite straightforward. Now, let's look for the frequency method. Now here, we can use the body diagram here, so the body plot of GS, and I can also borrow some code from somewhere like here. Well, maybe let's directly use this one from, yeah, let's use this one here. So the reason why I can do this is the following. So GS, and I think that this is sufficient, but let's make it a big one. And I'm taking the body of GS, which is the actual system, by the way, not the Putty approximation. I have the magnitude, I have the phase. So does anything change about the fact that I'm looking for minus 180 degrees? So should be equal to minus 180 degrees. So does anything change about this? No, because it doesn't matter if it is a system with delay, if it's something else. I have a body plot. I have a gain and phase plot versus the omega, the frequency, and that's it. That's all I need. I can look for the phase angle and the frequency where the phase angle becomes negative 180 degrees, and that's it. At that point, I can look for the gain and take the inverse, and that's my interval. At least that's my upper bound. So nothing changed really, and I'm using omega, mag val, and phase val, and for k val, I can conclude that this should be 1 divided by mag val. So let's see what the result will be. And as you can see, it is 7. Now, in GS, we don't have any delay. So if we use GST, since that has the delay part, let's see what the delay does to the system. So you can see that this is 0.9975, which again shows that we didn't calculate the interval for the first order partial approximation accurately, because there's a slight error there, because it should not be less than 0.9975. So the body diagram tells us that the interval here is 0.9975, or at least the upper bound is 0.9975. And the k-value that we've acquired from the second order partial approximation seems to be 1.03. So it shows us that this is an upper bound on the actual upper bound. So it's a rough estimate, and therefore, if you can, you should use the body method. Now, of course, not always you will not always be given the delayed body diagram. What if you have GS itself? So that becomes an issue, because if we remember, we are looking at the argument of g omega times exponential minus s. This is what we need, so basically j omega. So this is what we need to look at, minus 180 degrees. But what we actually have is arc g omega. So we have to take this into account. Of course, the gain plot does not change. We've talked about this. If you take the absolute value of the multiplication of this, it does not really change. But in terms of argument, I can say that this argument plus the argument of this, so the exponential term, should be equal to 180 degrees. So, of course, it's pretty obvious if you use cosine omega plus j sine omega, and the argument of this is a tan sine of omega divided by cosine of omega, and this is tan, so therefore this is the tangent of omega, and the a tan of 10 is basically omega. So therefore, since this is also negative, we can see that we have minus omega here. So this is a bit tricky due to the fact that I'm looking at arc g omega, and I try to determine what omega is. So basically, omega star should be written here. So I'm looking for omega star, but I am looking at arc g omega star. Now, I have only this plot here, arc g omega, and if I take this equal to 180 degrees, let's say this is 180 degrees, and this happens at, let's say, omega equals 2, then I am at minus 182. Or, by the way, not really. Let me show you why. Because this will be in radians, and this is degrees. You can't really do that. You have to multiply with 180 divided by pi. So that's also important. So let's see what this basically is. So it's 57. So we can say that this is 57. So if this happens at omega 2, then I'm already at the wrong place. So I should estimate a lower bound. Let's, for example, take, I don't know, 0.5. So having a low estimate of 0.5, we should look at the argument at 0.5, so omega star. So we have to use trial and error here. We should use 0.5, look for the argument at 0.5, and since 0.5 times 57 gives us 28.5, if we're lucky enough, the argument minus this should give us 180 degrees. If it's too low, we should increase omega. If it's too high, we should decrease omega. And in 3 steps, most probably, we should end up with the actual omega where this is satisfied. As I've told you, the challenge here is that you are given the body diagram of the actual system, and the delay is added afterwards, and then you have to take that into account. So you have to deal with this equation here via trial and error. So you can try it on your own. Basically, I have the documentation here. We look for minus 180 degrees. It happens at 2.45 approximately. And then this gives us 7. Now this was the actual interval in A. We again look at minus 180 degrees, but this time we are using the delayed one. And you can see that it is quite different. This has 250 here, minus 250. Here we have basically 150, but this is very much close to the point where we have omega equals 1. And here it goes down and down. Here we have a much higher value. So we are operating somewhere here. So therefore it's zoomed here, but actually this goes to minus infinity once omega becomes bigger and bigger. So this is basically a zoomed version of this. And you can see now that the result here becomes 0.99621. So the step responses are compared here, and you can see that you can come to the conclusion that the Paddy approximation, the root-locus method, does give an upper bound. It is a rough estimate of the actual stability bound, but the frequency method does provide you with the actual stability bound because it uses only the argument and nothing else. So we've seen how to basically calculate the stability interval of a system that has delay.